Okay, let's restart. We just showed the theorem, which means that the time-space class, time-space n epsilon n alpha is a subclass of linear hierarchy, where epsilon is less than 1 and alpha is a natural number. And also, the class of log space is a subclass of this time-space class. So this is the same as the proof in the lecture for P space. P space is a subset of exponential time. So this one is basically the same proof, and this epsilon here can be taken arbitrarily small. So we just show that the log space is in linear hierarchy, and the graph of plus, times, and less than equality are computable in log space. So they are all in linear hierarchy. So we have our result, which is linear hierarchy is the same as delta zero, a definable subset of natural number. So here are some remark. The first thing is, all right, although we have this correspondence, but it is still open that whether this delta zero hierarchy or the linear hierarchy is a strict hierarchy. Here, the delta zero hierarchy means the hierarchy formed by the delta zero set by counting the number of the alternate boundary quantifier. And the second one is if you are working in the models of arithmetic, you know that there is some highly non-trivial consequence concerning the n extension. If we know that this hierarchy is probably collapsed in some weak fragments of arithmetic, namely this I delta naught implies the collapse of delta zero hierarchy. Okay. So similarly, we could define the polynomial hierarchy. We can say that a set is in sigma NP if and only if it has this form, where this existential P stands for this X, and the length of X is bounded by some polynomial in the parameter, in the length of the parameter, and this R is in the class of P. But the problem is this quantifier, we cannot express it in arithmetic in an easy way. So we may write it down. So x, let's say is y squared. And we take the exponential for both sides. Because the length of x is roughly like log 2x. We take the exponential, we get here as x less than 2y squared, which is basically y to the log y. Okay, so let's start. So here we already show that class of time space and epsilon and alpha is in linear hierarchy, where epsilon is less than 1 and alpha is natural number. And this class contains all the log space. So this is the same proof for the same as P space. It's a subset of exponential time. This is basically the same proof. and the epsilon can be taken arbitrarily small here. So concerning these two steps, it just shows that the graph of this thing can be verified in log space, and the log space is in linear hierarchy. So all the delta zero definable formula can be verified in linear hierarchy. So that's the whole proof of this result. The linear hierarchy is the same as delta zero definable subset. And here's a remark. The first thing is it is still open that whether this delta zero hierarchy or linear hierarchy is a strict hierarchy. So here the delta zero hierarchy means the hierarchy formed by delta zero sets by counting the number of alternate bounded quantifiers. And the second thing is there are some non-trivial consequences concerning the extensions of models of the arithmetic. If we know that delta zero is probably collapsed in some weak fragments of arithmetic. So it would be I delta naught. This is a weak system of piano arithmetic, which we will see later, implies the collapse of delta zero hierarchy. And this is a very non-trivial and important object in models of arithmetic. Okay. Next, we shall talk about a bit of polynomial hierarchy. So similarly, we can define the polynomial hierarchy. Say the sigma NP set it can be expressed in this form, and this existence P means there exists X such that the length of X is bounded by some polynomial in the length of some parameter here, and this R is in P. But the problem is, unlike the linear hierarchy, we cannot express this bounded quantifier in an easy way in arithmetic. So, for example, we may write it as the length of x is bounded by y squared, and since the length of x is basically log x, right? And we may want to take the exponential, so we take the exponential to x less than 2y squared. It should be x less than y to log y. And this thing is quite hard to describe in arithmetic in a very easy way. But we will adopt another formulation by Samuel Bass with some new function. So basically, we will have a new symbol to characterize this function. So it will be easier to introduce some weaker system in arithmetic to describe the polynomial hierarchy. We will do this later, but here we will have another relation between the arithmetic and complexity. So first we shall introduce the first order arithmetic. So here's the first order arithmetic. What we want to do is to characterize the properties of the set of natural numbers. So we know that the set of natural numbers satisfy some rules or axioms. So here's some algebraic part of the axiom. So we may write it as when the x and y, x plus y is the same as y plus x, or right, when x, y, z, x times y plus z is the same as x times y plus x times z. So these are called the algebraic part of the piano axiom. What is more, but the more important part is the induction part. So we all know, the mathematical induction in natural number. If we have a property phi, and we know that phi 0 is true, and also we know that for any x, if phi x is true, then phi x plus 1 is true. Then 0 implies 1, 1 implies 2, 2 implies 3, etc. And we know that for any x, phi x is true. This is called the induction schema. But here notice that we only state this induction schema for all formulas phi, and not for all the properties of natural number. And actually, this piano axiom can form an infinite hierarchy if we restricted the induction schema only on a limited class of formulas. We may define this I sigma n to be the algebraic part plus the induction schema for all the sigma n formula phi. So here in this induction schema, we only allow that this phi is in sigma n. And similarly, we can define this B sigma n is the I sigma 0 plus the collection schema for all the sigma formulas. So collection schema means if for any x there's a y, phi is y. So we think of phi as a function from x to y. If for any x less than a, there's a y, then there's an upper bound for all the y. So there's b such that for any x less than a, there's y less than b, phi x y. And PA is obviously the unit of all I sigma. Here are some remarks. The first one is actually this I sigma n and B sigma n they form a class of subsystem of PA, and there are some implication results. This I sigma n plus 1 implies B sigma plus 1, and B sigma plus 1 implies I sigma n. And all the implications are strict, which means that I sigma n does not prove B sigma plus 1. And the same thing for this part. And again, the problem is these systems are too coarse to analyze the class below delta 0, but almost all the complexity classes are below delta 0. So in the future, so in the next topic, we will discuss the corresponding induction relative-wise to the class below delta 0, which is called the bounded arithmetic. But here we will show one connection between this even stronger system and the complexity. I need to introduce some mathematics here. So here's a famous Hilbert's tensor problem. So he asks that, is there an algorithm such that given any polynomial equation with integer coefficient, we can effectively compute or decide whether it has an integer solution. So like given a polynomial equation bx 0, we want to check that whether it has an integer solution, then is there an effective way to do this? So this is the Hilbert's tensor problem. And in the 1960s, a Russian mathematician Matyasevich showed that this is not possible. So this is Matyashevich's theorem. No, there's no such algorithm. But actually, it proves something stronger than this. It shows that actually to answer this question, you may need the very strong computability, almost like the Hawking problem. So here is the MDRP theorem. So M stands for Matyasevich, and DRP is the three American mathematicians. So it says that for any sigma 1 formula phi is variable, so sigma 1 formula phi means that there is x theta xy, where theta is in delta 0, which means that theta only contains the bounded quantifier. Only bounded quantifier. Then there is a polynomial equation pxy with integer coefficients such that phi y if and only if there is x pxy. So you can say that this question is almost the same as the holding problem. And this MDRP theorem says that with the help of the unbounded quantifier outside, basically we can ignore the bounded quantifier inside. So yeah, theta has some bounded quantifier, but this p, it has no quantifier. This is the MDRP theorem. And even more, this theorem, this MDRP theorem, can be formalized and proved inside I delta naught plus x, where this x denotes the totality of the exponential function. So it just says that for any x, 2 to the x exists. And it is open that whether we can replace the axiom x by some weak assumption, by some weak assumption here. You may think of this question as not that essential, but if the answer is yes, then quite surprisingly, there's some non-trivial consequence in the complexity, namely NP is the same as CoNP. So what is the weak assumption? So let us note this is called the axiom omega 1. It says that the x function, x to the log x, is a total function. So it says that for any x to log x exists. And notice that x to log x is greater than y if and only if we take the log here, we get the square of length x is greater than the length of y. So basically, omega 1, this axiom, it captures the polynomial growth of the length of x. So you can say that you can see some similarity between here, the omega 1, and what we define in polynomial hierarchy, right? And here's the theorem. It is by Rocky. If I delta naught plus this omega 1 implies MDRP, then NP is the same as CoNP. So here notice that omega 1 is weaker than exponential. We need one more tools to establish this result. It is called the Parek theorem, which is a bridge to connect the arithmetic and complexity theorem. Here is the Parek theorem. So if f is a delta 0 definable function, theta is a delta 0 formula. If I delta 0 plus, if this is basically says that f is a total function. F is total. If I delta naught plus f is total, can prove that for any x, there is a y theta xy. And I delta naught itself proves that f is monotone, then there is a term or polynomial T with the symbol F such that I delta naught plus this total T of F implies that for any X, there's the upper bound for this Y such that theta xy. So basically it says that this Y can be bounded by some term in F of some X. There are two things to notice. The first thing is this X log X can be expressed in the delta zero formula, and I delta naught can prove it. Can prove that it is monotone. And the second thing is T with symbol F. So here the symbol F is actually X log X. So Y less than Tx is equivalent to the length of Y is bounded by some polynomial of the length of X. So this one is basically the same as here. Yes, it's basically the same as here. So I shall give a sketch of the proof of this part theorem. So if the inclusion is false, which means that for any term, this theory, I delta naught plus that's my mistake. I should add for any x, there is y, fx is y. So if not, then for any term, this I delta naught and the total t of f, and the negation of the conclusion is consistent. Consistent means that we cannot derive a contradiction from this theory. And then we can take a new constant c here to witness this existential point for x. And the theory becomes I delta naught plus for any y less than tc, not cy. And I should also add for any x, there is y fx is equal to y here. This is consistent for all term t. And we need to use one tool in model theory, which is a compactness. So actually this theory is also consistent. So we have an integration of all the terms with symbol f. It says that I delta naught plus for any y less than t1, you cannot find this. We have not theta cy, and also for t2, there should be t2 here. And the same thing for t2, etc. for all term of for all the term ti. And because it's consistent, then we can take a model of theory, which I call it M. So M is a model of arithmetic. It is linear. This is M. And here is our constant C here. And we take and we let K to be the closure of C by all the term in F. So here is our K here. So there are some term. There's TC. Let's say there is T prime C, and K is the closure of all the term T applying to the C. And next, we can easily verify that K satisfies the I delta naught, and the totality of the function f, because k is the closure of all the term t of this C. But k does not know that, but k cannot find that it should be not exist, as k cannot find such y such that theta cy holds. But because by the theory above, by the theory here, we know that any y would be above any term in C. So such y would be here. So this any witness y would be above this k. And this would be the contradiction to I delta naught plus f is a total function implies for any x there is a y theta xy, because by there's no y theta cy, and here's a contradiction. I think we may just let this parasite. We may just take it for granted for this part theorem. Okay, let's show how to use this part theorem to get the result. Next, we shall use one fact. We shall use that the set of this set is NP complete. So I think this is the simplest NP complex set in arithmetic. So the triple ABC such that there is YZ to satisfy this equation. This set is NP complete. And we let this phi to be x is the code of this triple and the negation of z. So this one would be CoNP complete. Right. And we can see that this phi is in delta 0. Right. And now we can use the MDRP signal for this phi. So phi is equivalent to some y. So phi is equivalent to the exists y such that some polynomial of pxy is equal to 0 for some p. And if this implication is true, it is provable, then by Parik's theorem, we can find some t with this function symbol to bound this with this y. So we may write it as phi x if and only if there is y less than x log x, say pxy is 0. And if we replace this one by the form in the polynomial hierarchy, it will be here. So phi x if and only if there is y and the length of y is bounded by some polynomial in the length of x such that pxy is 0. And this one is, and verifying this is in the class of the polynomial time. This is in P. And here this, and here it is correspond to the sigma 1 definition. So this one is in NP. and phi is in NP. So it just shows that a CoNP complete set it is in NP, which means that CoNP is actually the same as NP. And actually, we can start with arbitrary CoNP set, but it will becomes a bit more difficult here. And here is the only one remark. It says that we can do exactly the same thing if we know that either the nut, itself proves this MDRP. Then actually, not only the polynomial hierarchy class, the linear hierarchy. So if either the nut itself proves this, then this y here, this y will be less than some polynomial in x. T is a polynomial. And if we take the log, it means that length of y is less than some linear term in x, which corresponds to the linear hierarchy. So if the implication holds only for only either the not without any further assumption, then by the same method we can show that the linear hierarchy collapses to the first level. So this is the quite surprising connection between arithmetic, the implication of weak arithmetic principle, and the result in complexity.